Polar areas, part 2, area between curves. Consider the graph r equals 2 minus 4 sine theta. I have drawn it for you on the left. We want to find the area outside the small loop, but inside the larger loop. We'll use symmetry to do this. We'll get 1/2 and then multiply by 2. So your thought might be, why don't we just find the area of this larger loop like such? Notice that if we do this, that area will include the smaller loop as well. So what we really are going to need to do is find the area of the big part and subtract out the area of that little part. Before we begin, let's start getting limits, or at least points that I think might be helpful for us. You can do a little bit more work to confirm that what I'm saying is true, but I think we've done enough graphing to know that we're going to start over here when theta is 0 and go counterclockwise, as we tend to do. We hit the x-axis again at pi, of course. And then we're going to hit the y-axis at least at pi over 2 and 3 pi over 2. But it looks like we're actually going to hit it a bunch of times. So if this is theta equals 0 over here, and we're going counterclockwise, when is the first time that we reach the origin? Well, that, of course, is when r equals 0. So solving that, we get sine theta is 1/2, or theta equals pi over 6. And then let's continue on the path. So I'm over here, and then I'll reach the y-axis. Well, of course, that's at pi over 2. We've discussed y in previous videos. Keep going back up again, and I'll hit the origin when sine theta is 1/2, or at theta is 5 pi over 6. And continue around past pi, hitting the y-axis again at theta equals 3 pi over 2, and then back up to where we started at 2 pi. So this should be enough for us to be able to do the problem. Now, honestly, the problem is going to get kind of messy. So, we want to find the area, which is going to be the area of the larger portion minus the area of the smaller portion. That is the larger loop and the smaller loop. So we need some bounds. And I'm going to do the left half only and then double my answer. So let's see what we get. The area of the larger loop on the left, well, let's just do the total, is 2 times the left half, right? So 1/2 integral of r squared d theta. The 2 and the 1/2 will cancel. So what are my limits? Well, I start here at 5 pi over 6, and then I go down here to 3 pi over 2, and those will be my limits for the larger loop. How about for the smaller loop? Once again, 2 times 1/2, so I won't write it. Same thing inside. That is, my integrand will be 2 minus 4 sine theta squared, the d theta. But what are my limits on the smaller loop? Well, it's here. First time I reach the origin, pi over 6. And then down to here. Remember, we're only doing the left half, so pi over 2. All right, now we got to do some work. So let's find the area of the larger loop. Which is going to be the integral from 5 pi over 6 to 3 pi over 2 of, and we got to multiply this out. So I have 2 squared minus 2 times 4 sine theta, but twice, and then plus 16 sine squared theta d theta. We need to rewrite this part. Recall that the sine squared of theta is 1/2 minus 1/2 cosine 2 theta. So I could write this integral as 5 pi over 6 to 3 pi over 2 of what? Let's see. 4 minus 16 sine theta plus 16 times 1/2 minus 16 times 1/2 cosine 2 theta. And now we can integrate this one. So I'll get 4 plus 8, so 12 theta, and then plus 16 cosine theta. And then minus, okay, we have sine of 2 theta. And it's not 8 because we do a u sub technically, so we'd have 4 sine of 2 theta from 5 pi over 6 to 3 pi over 2. Plug in the top limit, we would get 12 times 3 pi over 2, so 18 pi. Plus the cosine of 3 pi over 2, 0, that's nice, minus 4 times the sine of 3 pi, also 0. Now let's plug in our lower limit. Minus 12 times 5 pi over 6, so that gives us 10 pi. Plus 16 times the cosine of 5 pi over 6, which is negative root 3 over 2. And then minus 4 times the sine of 5 pi over 3, which is also negative root 3 over 2. If you need to, go in to stop the video and confirm that these values are correct. So we get 18 minus 10 pi. And then back here we have minus, I'll write it right here so we can see it, minus, and then we have negative 8 root 3, and then plus 2 root 3. So minus a negative 6 root 3, so plus 6 root 3. That's the area of the larger loop. Area of the smaller loop is same antiderivative, 12 theta plus 16 cosine theta minus 4 sine 2 theta, but from pi over 6 to pi over 2. And just for the sake of time, I'll put down the answer. In this one we get 4 pi minus 6 root 3. So the area that we want, that is the total area, is the larger loop minus the smaller loop, which gives us 4 pi plus 12 root 3. Let's take a look at another example. And for the sake of time, let's set up but not solve an equation that gives an area common to the graphs r equals 1.5 and r equals 3 cosine 2 theta. I have drawn the graphs on the left. So the circle is r equals 1.5, a circle with radius 1.5, center at the origin. The petal graph is r equals 3 cosine 2 theta. And what I've done to help us see what to do is I have blown up the first quadrant, and only part of it. So I'm really blown up this part and exaggerated it so we can see what's going on. I didn't do the top part here. But I want to find an area, and it'll be this piece here. That's what I've drawn in the graph on the right. And to find the final area, I just need to multiply it by 1, 2, 3, 4, 5, 6, 7, 8. So let's find this blown up, exaggerated portion in the first quadrant. And here's something that I highly, highly recommend. When you're doing areas like this, draw a ray from the origin through the intersection point. The reason is to make something very visual that we're going to need in just a bit. So let me change some colors to help us see it a little bit better. Notice that the area that I want has two parts. I have this top part, which I'm coloring in red. And then I have a bottom part, which I'm coloring in blue. And if you look really carefully, I can find the blue portion using the graph r equals 1.5 only as a portion of that graph. And the red part, I could find that area by using the graph r equals 3 cosine 2 theta only. If you need to, stop the video and take a look and see how that works. That this red part is a part of only that graph, and the blue part is only a part of the graph r equals 1.5. And I draw that ray to help me see things more clearly. That is to distinguish the parts. Now, of course, I need some limits. Well, the nice thing about these graphs is they both start over here at theta equals 0. That's for both of these pieces. They both graph in the same direction. Because sometimes they start at different places, sometimes they graph in different directions. Sometimes one graph takes longer to graph, whereas both of these take 2 pi. So the problem's complicated enough without adding all those other variables. Now, I need to find the intersection point. It's probably going to be one of my limits on integrals. And of course, we can find the intersection point by setting the graphs equal to each other. So 3 cosine 2 theta equals 1.5, or the cosine of 2 theta is a half. And that's when 2 theta is pi over 3, or 1 theta is pi over 6. So the intersection point is theta equals pi over 6. So the area of the blue portion is 1/2 times the integral of 0 to pi over 6 of 1.5 squared d theta. The area of the red portion is 1/2 the integral of 3 cosine 2 theta squared d theta. But from where to where? It's not 0, because I start at 0 here, I'm going this direction, and so my lower limit is going to be pi over 6. Oh, what's the upper limit? When do I reach the origin? That's, of course, when r, 3 cosine 2 theta, equals 0. Or the cosine of 2 theta is pi over 2, or theta is pi over 4. So what is the total area common to the graphs? Is exactly this times 8.